Bem-vindos a todos ao nosso seminário de hoje, no dia 15 de setembro de 2021. É um prazer tê-los aqui conosco. Só a informação padrão, não é? Essa palestra será gravada e publicada no YouTube. Então, se você não quer ter sua imagem e sua voz gravadas e divulgadas na internet, por favor, desligue seu microfone e seu vídeo agora e interaja conosco pelo chat, tá bom? Eu posso transmitir as suas perguntas para o palestrante. Sua permanência nesse vídeo indica concordância e consentimento para a publicação, sua publicação no YouTube. Okay, so thank you all for coming. I was just saying in Portuguese that this video is being recorded and it's going to be published on YouTube. So if you are not happy with your image and voice being recorded and published on the internet, please interact with us via chat, okay? But if you decide to stay, you're giving us a heads up, an okay for us to publish this video on YouTube. So it is a great pleasure today to have Karol Bacik from now the University of Bath. I met him at the University of Cambridge when he was working on his PhD with Natalie Vriend and Colm Keeley Caulfield. It was very nice of Karol to accept the invitation to give this talk. He was doing a very nice work on dunes and they let's say not quite romantic relationship, right? In a very confined and prepared setup, and he's going to talk to us about that today. So as I said before, these talks are extremely informal, so please feel free to interrupt the speaker at any time. It is better if you do by opening your microphone and saying asking your question directly to the speaker, or if you prefer, you can raise your hand and I will interrupt and give you the word for you to ask your question. Okay? All right. Karol, thank you so much for coming. It is a great pleasure to have you here. You can start your seminar right now. Thank you very much.
Great. Thank you very much, Yuri, for the introduction, for the invitation. It's a great moment for me as well, because that's the first talk I'm giving in South America. So let me try to share my screen now, and we may start. I did it before, so right. Can you see it all right now?
Yeah, it's working. Yeah.
Okay, great.
If you just could minimize the little video there.
Yes, we'll minimize this, and that should
Perfect.
be perfect. Okay, so yeah, that's me. I'm Karol. Yuri already introduced my supervisors. Here they are in pictures, and that's me doing experiments in granular mechanics under the supervision. And this talk is going to be about sand dunes, and more precisely the dune fields. So here is a beautiful example of dunes from the Arabian Peninsula. These are so-called Balkan dunes with the characteristic crescentic shape with the horns pointing in the direction of dominant wind. This is also the dominant direction of motion, here indicated with the white arrow. Because sand particles are picked up by the wind, and over time this could cause dune migration, and the topography can evolve. This can be interesting, for example, if you have a road somewhere down this picture, or worse still, a house. These things do not exactly happen overnight, but over a sufficiently long time scale, they can become important. So predicting I should also say there are sometimes dunes underwater, and here they can also interact with various pieces of infrastructure, pipelines, cables at the bottom of the sea. So predicting the evolution of the dune field topography can be important or interesting, but how could we do it? So one way of doing it would be to get hold of a map. So try to map the topography at every point in time, at every point in space, and then write down a big PDE which involves all the physical processes and hope that we can understand how it evolves. Then can be difficult. So an attractive alternative of such a big system would be to appreciate that this dune field is actually composed of individual heaps of sand. So maybe we could give a decent reduced representation by just keeping track of the position of each dune and how big it is. Because, you know, you've seen that they tend to have a similar shape, so maybe just giving one spatial dimension like height would be enough for each of the n dunes in our field. And then our horrible PDE becomes a horrible ODE, where the migration rate, so the advance of the dune, and the height depend first of all on the local properties of the dune, and then potentially also on the interactions between them. So this kind of ODEs may be what we will be trying to think about today. But of course, what I'm going to actually talk about is not going to look anything like a real dune field. I'm going to consider an idealized experiment. So first thing we'll do is to define the experimental setup. Then I will, in one slide, give you the flavor of the kind of continuous modeling, PDE modeling, which could be involved in sand dunes. And then we'll move on to this reduced dynamical system and try to study its properties in this toy example. And if there's time, there will be a bonus second part of the talk. If you've read the abstract, you may anticipate what it is, but only if there is still time. So that's the laboratory. Here's our experiment. It's a big, well, 2 meters in diameter tank. I will try to start the video now. So you've seen that instead of driving dunes with wind, we're driving them with water current. And our dune field is replaced by this narrow channel. So this is a narrow channel filled with water. The interesting feature is that it's not straight, but it's wrapped around the circumference, so it's circular. It's one of the rare occasions of periodic boundary condition in an experiment. It stopped rotating, but maybe I can try to. Okay, some things. Can you still hear me? Am I still here?
Yeah.
Okay, that is just the slide which got funny. Okay, sorry, we'll go back. Okay, so you've seen how it rotates, hopefully. The idea is that it rotates, and the rotation of this paddle induces the motion of water. And the current, if it's strong enough, it can pick up these sand particles which form these little heaps. These are the dunes. These are this is the laboratory version of the sand dunes.
So both the paddles and the base rotate, right, Pavel? Right, Karol?
Yes, that's correct. Okay. Or
yeah. Okay.
If you start again, both of them rotate, which is well, it's obvious the top has to rotate. It's not obvious why the bottom would have to rotate. First of all, it's convenient because then the entire bed periodically comes into our field of view, so we can have just one camera to observe them, and then we can scan the entire topography at every revolution of the turntable. The second thing is that actually in this rotating flow, you need to somewhat manage the centrifugal forces and potentially some secondary flows. So actually, by tuning properly the ratio of the rotation of these two elements, you can ensure that, to first approximation, as best as possible, the dune is really quasi-two-dimensional. That's the distinct feature, that we're no longer talking about Balkan dunes, but they are confined into this narrow channel, and they are kind of level across this 9 centimeters wide channel. So these are quasi-2D dunes, which we'll be talking about.
Right, but you only see the dune once at a rotation. Your camera is not turning with the table.
There are 2 types of cameras. So now we're looking at the camera which is fixed in the laboratory, and here only a dune comes every 1 rotation. So for processes which are relatively slow, this is good enough. If you're interested in what happens at a sort of smaller scale, you may attach the camera also to the table. So now it co-rotates with the table, and the only thing which moves in this frame of reference is the dune. So here you can see the dune coming. It enters the field of view, and here is its steep downstream edge. It's held at the angle of repose of the granular material. And here there was the crest, the tallest point, and now there's a shallower upstream face, and that's how it migrates. The bulk of the dune is immobile. That's an important point. It's only the narrow layer of rolling and sliding grains at the interface that actually moves. So the dune crawls up on itself, and now it's gone, and it left clear ground behind it. So it moves on bare substrate. Okay. Does that answer your question about cameras?
Yep, perfect. Yes.
Okay, so that's what. So you've seen the dune, and now how can we understand its motion? So this is what the dune looks like. All the grains moving, and we can have it has some sort of topography profile, as I said, steep downstream phase, shallow upstream phase. So this is some sort of h as a function of space and time as the dune moves. The second function of space and time you may consider is the sediment flux. So how many grains cross an imaginary control volume per unit time from left to right, say. And these two functions kind of completely describe this quasi-dimensional dune, and they are related because of conservation of mass. You can write down this very simple equation, which is known as the Exner equation, sometimes in this field, which relates the changes in height to the spatial gradients of flux. So if dH by dt is negative, it means it's called erosion. That means that we're digging down the dune, and then the erosion must enrich sediment flux. Conversely, positive dH by dt means deposition, and the grains must have been deposited from the flux. So very simple equation in 1D. If you rewrite it in this slightly cheeky form, which almost always works, with a bit of chain rule, you can pretend that it's an equation just for h, just for the height. And this is a very particular equation, sort of quasi-linear, kinematic wave equation, I call it here. And you could, if you knew this value of this quantity, dq by dh, you could try to solve this equation with something like the method of characteristics. This is kind of the wave speed of the system. I'm not going to try to solve it, but we can still use this framework to interpret some of the experimental data. So here's an experimental data plotted in two different ways, but it's exactly the same thing. So let's look at the top first. This is a space-time diagram. Here's space on the x-axis, there's space, and this time goes up. It's normalized in a certain way, and this is the beginning of every of my experiments. This is a quasi-triangular heap. I put a heap which is a triangle, and then over a characteristic times, it rearranges into its characteristic dune shape, and then it migrates as a sort of coherent structure. So, and each line corresponds to my one scan of the bed at one revolution of the turntable, actually. So now at the bottom, it's exactly the same data, but plotted as a contour plot of height. So here, these are these contours, 1, 2, 3, 4, 5 centimeters. It's how tall this dune actually is. And if you look one of these contours, so like level of 2 centimeters, from the point of view of the conservation equation, this is the kind of characteristic. This is the line of constant height, and the wave speed is the gradient of this line. It just happens to be. So initially, there are a lot of actually nice analogies here between sort of gas dynamics and waves and nonlinear waves and the sand dune. So it behaves according to this equation where the wave speed controls, well, the wave speed. So initially you can it sort of fans out, and then it starts migrating as a coherent thing. The distinct feature of the steady state, the definition of the steady state, is that these characteristics, all these world lines, are parallel. If the dune moves without changing shape, it just shifts. It's equivalent to saying that all of these lines are parallel, which means that the gradient dq by dh must be constant. And that's the one fact which I will use now to prove something which I mockingly call the fundamental theorem of sand dunes. So in a steady state, the dq by dh is constant, therefore I can approximate it with any finite difference I like. For example, the finite difference of flux between the crest, so the tallest point of the dune, and the upstream edge, bxb, and the same difference at height evaluated at these 2 points. So now the flux at the crest is quite large, the influx is potentially negligible, and difference of heights between the top and the bottom is by definition the sort of height of the dune. So all else being equal, smaller dunes should be faster because the migration rate of a steady state dune should scale as 1 over the height of the dune. So this denominator is everyone's favorite expression. If someone knows one thing about dunes, it's probably that small dunes move faster. However, we shouldn't forget that there's also this numerator, which tells us that the migration rate is also proportional to the difference of fluxes, which can depend on the flow in a complicated way. Okay, so that's the only thing which you really should take away from the slide, that we have an expression for the migration rate which is proportional to the difference of fluxes, inversely proportional to the height of the dune. Is that all right? So now I will just take this and carry on to the reduced model, where we will represent dunes not with a continuous h of t and continuous q of t, but maybe with just 2 numbers for each dune. Actually,
can I ask a quick question, Karol, before there? So on your spatial-temporal diagram there, so that dune that you plotted, is it a small dune or is it a large dune for your experiment?
It's an average type of dune.
Average dune. So is it the case that in larger dunes you never see a steady state? So is it the case that with larger dunes the flux will depend on h? So that the velocity is not constant.
So within my so you see the velocity is not constant at the beginning here.
Yeah, right? Because that's the unsteady part, right?
Within my experiment, I can all sizes of the dunes reach a steady state.
Okay.
After a rearrangement period which is relatively short, so sort of 1 turn over time. So the dune to travel its own length, it's usually quite close to its steady state.
All right.
Okay, so I usually reach this steady state, and these sort of steady state dune is actually what we'll be concerned about now, or quasi steady state of a dune. But now one dune is a little bit boring, so let's have 2 sand dunes. This is already the simplest dune field you may have when you have 2 dunes interacting with each other. Then the real dune field will have many more, but 2 is the sort of fundamental building block. And now in a reduced way, we'll represent each of them with just 2 numbers. As I said, just its position, and in my 1D domain, it will be just 1 number, and its size. And here, a convenient way of characterizing size will be the cross-section area A of my quasi-2-dimensional dune. And there will be the second dune positioned at x2. And by conservation of mass, I could calculate the size or the cross-section area of one dune from the cross-section area of the other by subtracting from some total capital A. Now, so in principle, there are 4 or actually 3 numbers here, but actually, given that my domain is periodic, I may say I'm only interested in the relative position of the dune rather than the individual positions. So I could look at the separation S, and the separation S and the cross-section area of one of the dunes are 2 numbers which completely characterize the state of my system of the 2-dune system at this level of resolution. If we don't care about the actual fine details of the surface, I could describe the 2-dune system with just 2 numbers, where the separation goes from 0 to 2 pi r. So in the top right, you can now see the sort of phase diagram where all the dynamics can happen, separation going from 0 to 2 pi r, and the mass going from sort of 0 to its maximal value. So this is the world where this system lives. Some interesting properties because of the one property you may find because of the rotational symmetry. There's this point of symmetry. Oh, this is a very distinguished position of 2 dunes of equal size separated by pi r. Now, if you go, there's a point of symmetry of the system. Now, if you go towards the right or left from here, then one of the dunes gets really small. And when it gets small, it can get unstable. So the right and left boundaries can be a little bit dodgy. Similarly, the top and the bottom boundaries means 2 dunes are the separation tends to zero, so maybe describing them as two distinct structures no longer valid. So we would be really mostly interested in the center of this phase space. But now the question is, what kind of dynamics can the system assume in this two-dimensional system? So here our main ingredient is, of course, the fundamental theorem of sand dunes. If you remember, expression for the migration rate. So the difference, the time derivative of separation is just the difference of the two migration rates, and the time derivative of the size will be the difference of influx and outflux to the particular dune, and actually we're already committed to the conservation of mass. If we assume that the transit time of particles to get from one dune to the other is relatively short, we can actually say the influx at one dune is the outflux at the other. So we have expression for S and A. Now, with a couple more assumptions, we can try to close the system. So if we assume that dunes are self-similar in shape, we can say that height is proportional to the square root of area, because area is the variable I have in my system rather than height. Now, they are immersed in one flow, in one channel, so maybe it's the same flow producing the sediment flux. So maybe we could try to say that the flux is actually the same at the crest of both dunes, and that the inter-dune fluxes are relatively small. So let's say they are 0, and you have a beautiful system. It's a little bit boring because A dot is 0 in this system, so this variable doesn't change at all. S has a simple expression which depends only on A. Okay, let's make sure we understand it in terms of the simple phase space diagram. So A dot being 0 means we only move at vertical lines here, and the size of the velocity
don't change.
Sorry?
No, the sizes won't change.
So the size won't change. So this is the simple model which believes that the dunes are self-contained. So there's no way for them to change size. And it also believes very strongly this fundamental theorem of sand dunes in a simple version, that the migration rate depends on the size of the dune only. So whichever is bigger, it's slower. Now this is a little bit problematic because it means that almost with probability 1, the dunes are going to collide. One of them will be a little bit smaller, so we'll be drawn to this boundary of a dune-dune collision, either one way or the other. That's what this naive model predicts. The only chance that something potentially interesting can happen is if you start with dunes of equal sizes. Then you are at this neutrally stable line, but maybe there will be a random fluctuation which will take you away from here, and you're going to collide one way or the other anyway. So this is the only potentially interesting point. So let's try to simulate this experimentally. Let's try to start with two dunes of equal size and see what happens in the tank. So recap how we do this. We put two piles of sand. They quickly rearrange into the characteristic dune shape, start migrating, start moving, but then it turns out that they separate. So the separation changes, and actually here you can see this in a space-time diagram over a longer time scale, so the 3 hours. So in time 0, these two dunes were close together, and then they started migrating, both of them. But you can see that the downstream red dune had a distinctly higher migration rate. So it was faster. The blue dune was slower, maintained close to constant migration rate. As a result, they separated. And actually over time, they equilibrated at sort of pi r, so equal separation and more or less equal mass. So in terms of the phase space diagram, let's make sure we went from this dot straight up and stopped at pi r separation. This is completely incompatible with this model. Or you can say, oh, maybe that was something random which took us away from here and we stopped here. There's nothing random here. I've repeated this experiment about 100 times, and it's always like that the dunes start close together, but then over time they when the dunes start close together, over the time they would separate and converge this antipodal configuration of two dunes of equal size, but separated by pi r, as far as they can be away from each other. They kind of don't like each other. So what have we missed? And they really stay there. So here you can see the separation as a function of time. I ran that experiment for 10 hours, and they are really kind of stay there modulo some oscillations. So what have we missed here? We've missed the interaction between these two dunes. So from the hydrodynamic point of view, the red dune is in the wake of the blue one. So when the flow meets one of the dunes, there's the recirculation bubble, and it's a high Reynolds number flow. There's all sort of turbulent mess being produced here. And these turbulent flat structures can be advected by the flow. And when they impinge on the surface of the next dune, they can change the properties of sediment transport. You can realize that by looking closely at the surface of these two dunes. So the upstream dune, well, you look closely, you can see, well, the sand and water separated by this narrow layer of rolling and sliding sediment. Here it moves in a sort of nice laminar fashion at the upstream dune, whereas at the downstream dune, the surface is kind of almost boiling in that the continuity of sediment transport is interrupted by these intermittent sweeping events. So you should think of it that there was an upstream dune which generated some turbulent structure. It impinged on this dune, swept sediment. And this way we are enhancing sediment flux and therefore the migration rate of the downstream dune. So our naive model missed the hydrodynamic interaction between these two dunes, which turns out to be very important in the experiment. So let's try to be, does that make sense? Maybe that would be a good question, a good place to pause for a second.
Yeah. So in fact, both dunes will shed a structure, right? Will shed a vortex out
Correct.
of its crests. So when you see the smaller one trying to catch up with the larger one, how do you explain this? Let me rephrase this. The flow direction matters a lot, right?
Oh, yes.
So the flow direction, so that the smaller one can catch the larger one, it's a flow coming from the larger one to the smaller one, right?
Okay, so they are in a periodic domain.
Yep.
So they are and they are both shedding these structures. So now it's a matter, in this first experiment I'm showing now, they are actually of equal size.
Mm-hmm.
We'll do small behind the big in a second. They are here of equal size, and it's about the asymmetric spacing, that this separation is small. So the red is experiencing more turbulent conditions. The red is also shedding some vortices, but most of them would dissipate before they reach the blue one.
So the flow is from the left to the right.
The flow is from the left to right, correct.
Okay.
The flow is from the left to right, and they kind of also would move in the direction of the flow. So it keeps sweeping sand from left to right. Mm-hmm. And here the distance between the dunes. Well, you need to, the relevant distance for the red dune is upstream of it. The relevant distance for the blue dune is this thing which goes across 2 pi.
Across 2 pi, yeah.
So it's relatively far away from the red dune, therefore there's this imbalance of the turbulent intensity.
So surely this scale will be much larger than the scale of this vortex bubble that is being shedded, and therefore the red is not seeing the blue, but only the other way around. Sorry, the blue is not seeing the red, but only the red is seeing the blue.
Or it's seeing it less. Yes.
Oh, it's seeing it less.
Yes, actually, you're right. I think you're right. The blue is not seeing the red.
Agreed. I see. I think we have a question, Danielle.
Yep.
Hello. Could you move on to the next slide, please? I have a question about the. Okay, so the second column, the one on the right, you put there when S is small, sediment transport at the upstream dune is continuous, and at the downstream dune it's intermittent. Okay, so with this mechanism, wouldn't we expect that the self-similarity condition is is going to be like negatively influenced by this mechanism, since I believe the downstream dune having intermittent sediment transport is going to perturbate the shape of the
dune
of the downstream dune on the red dune. And so at the same time, I believe that the distance between the dunes will enhance this mechanism, since I believe that if the dunes are too up close, then I believe you might have a greater self-similarity, but I'm sorry, the other way around. If the dunes are very up close, you might have smaller self-similarity, but if the dunes are further apart, then I believe that you get the self-similarity because the sediment transport from the upstream dune might not influence so much the downstream dune as if they were closer. I'm not sure if I made myself understand.
You're right. Yes. So there are a couple of assumptions I made before. One of them was that the shape of the dune is similar for these two dunes. Okay, and this is going to be violated a little bit because they experience different flow conditions, and the shape depends a little bit on the flow conditions too. But then the thing which matters for the way height and the shape enters into the migration rate expression is, remember, it was 1 over h, so just 1 over the top height. And now this assumption of equal height may be violated, but it's not the leading order violation, if I may say. So one of them will have like 5 centimeters and the other will have 5.1 because of turbulence or something. So that will be a little bit. What's more violated here is the assumption that they have equal sediment flux at the crest. Because I assume that there's a shear stress which is imposed by the flow, and it's equal for these two dunes, and that we have equal amount of sediment crossing per unit time. And this is the thing which is most directly affected by the turbulence, and this is principally why our model failed. Why we didn't capture it in this simplistic description. Does that make sense?
Yep. What is the Reynolds number we're talking about, Karol, here?
Sorry?
What is the Reynolds number we're talking about on this experiment?
30,000.
Okay. Okay. Based on the width of the
it's based on the height of the dune or the width of the channel, which is actually of the same order of magnitude and local velocity there.
Good. Okay. Carry on.
Okay. So let's carrying on now. Okay. So this was. We need to update our model. Just so we'll retain the self-similar shape. Sorry, that because I claim that's not the leading order problem. The leading order was our assumption about the equality of fluxes. So now we will say, okay, indeed they have some basic value Q naught, but they can be influenced by the upstream boundary condition. So there will be some sort of interaction function which can increase or decrease the sediment flux. And for the dune 1, so it's blue, the distance which matters, it's 2 pi r minus s, how far its upstream dune is, and how big, what's the volume, what's the cross-section area of the other dune. Symmetrically, for the red dune, it matters the separation to the crest flux can be influenced by how far the dune is as parameterized by S, and how big the blue dune is, which is A. And we can be also slightly more mature about these outfluxes. We'll say, okay, to first approximation, the dunes are self-contained, but with a small parameter epsilon, we will say that it's small but non-zero, this outflux, and it can also be influenced by the turbulence. So now with these slightly more complicated expressions plugged into our S dot and A dot, we get a proper dynamical system, which at least has some dynamics in both of the variables. Now, I haven't told you actually yet anything about these interaction functions, but we will not try to get into that because that would require proper experimental input, which we do not have. But some plausible features is that they are positive always, because we've seen that the flux is enhanced generically rather than suppressed by the turbulent interaction. We will say that it matters how large the upstream obstacle was, which corresponds to an appropriate partial derivative being positive, and that the influence decays away from the upstream obstacle, so another partial derivative is negative. Now, with these assumptions, now with a bit of trust, you can trust me that the phase space diagram will look something like this. Rather than this simplistic, 1D thing, we will have a proper fixed point. So the point of symmetry at dunes in antipodal configuration of equal size will actually be a fixed point of the dynamical system. It has to be. And it will probably be stable. And there will be this distinct slow convergence direction, what I call here the slow manifold. It comes from the fact that I assume that there's a small parameter in the system. I assume that there's an epsilon, which says that the mass changes slowly and separation changes fast in comparison. So a generic trajectory, I'm hypothesizing, will quite fast converge to this slow manifold and then slowly go to the symmetric fixed point. Okay, let's go from this abstract world to the experiment, which happens to do exactly that. So now we need to start at the initial condition, which is the purple dot. So this will be dunes at pi r, but one will be smaller than the other. We're starting with a small and big dune separated by pi. And there's a lot of things which happen here, but so first of all, they get close together. Because of the fundamental theorem of sand dunes, smaller are faster, so it's trying to get closer. But at some point, this turbulent feedback, wake-induced feedback, becomes important, and there's a point where they have equal migration rate. The blue is fast because it's small, but the red is fast because it's propelled or repelled by the blue dune. When they're sufficiently close, the red starts feeling the turbulent wake and it starts moving faster. But this is not an equilibrium yet because these turbulent fluctuations also enhance the outflux. They drain the red dune of mass. So there's a burst of sediment flux. Some grains leave the red dune across the periodic boundary, move and accumulate at the blue dune over a longer time scale. The red gets smaller, blue gets bigger, and they separate again. You can kind of see that they're already separating here after 3 hours. For technical reasons, I cannot show you the full space-time diagram, but here you have separation as a function of time. It's an actual experiment. The dunes got close together, and they slowly but surely converge to the antipodal configuration after about 10 to 15 hours, and then they stay there. And they are of equal mass. You cannot measure mass in real time, volume in real time with good accuracy, but you can do it at the end of the experiment, and they are indeed almost perfectly equal in mass. So they, no matter what you start from, they're trying to converge to this one attractive fixed point, which is dune of equal size and equal separation. Okay, how confusing is that?
That's very cool. Carry on, carry on. Any questions here? Okay.
Okay, so let's get slightly more mathematical, maybe, about this fixed point here. I claim that it's going to be stable. Can we argue that it's actually going to be stable? Where the linear stability of a fixed point, as we know, depends on the eigenvalues of the Jacobian matrix. I can linearize about the fixed point, and I could compute the eigenvalues in 2D. You can also equivalently just try to compute the determinant and the trace of the Jacobian. And I will try to argue something about that without doing any calculations now. So in our system, the Jacobian looks like this. Because we assume that the A dynamics is slow, the second row, all the entries from A dot have are of order epsilon, they are of small order, the S dot dynamics is of order 1 plus an epsilon correction. Because of this form, the trace is of order 1 plus epsilon correction. The determinant is of order epsilon plus epsilon squared, and that's it. In the simplest assumption, there's not plus dot dot dot. It's not an asymptotic expansion, it's an exact expansion of the system I proposed. And now if you look at this and treat epsilon as a parameter, you would realize that these two equations define a parabola in the trace determinant plane. So as we vary epsilon from 0, let's say, we are going to move along a parabola in this phase space diagram. So sorry, in this trace determinant plane. So for when epsilon is small, as expected, we'll be in this region, white region, which corresponds to a stable node, so a sort of steady convergence to a fixed point. But when it's increased, there's a possibility that we enter into oscillatory solutions, and if it's very large, the fixed point, the antipodal fixed point, will have the saddle characteristics, so we'll have a stable and an unstable direction. Okay, there's also a thing about how this parabola actually is oriented, whether we go right or up, or it depends on the signs of these coefficients, but you can argue plausibly from the system that it's going to go like this. Okay, so we've seen already an experiment in this region where it's a stable node. Can we do an experiment where the dunes are going to oscillate around the fixed point? It would correspond to increasing an epsilon. Now, unfortunately, in the experiment, there's not a knob in the lab which says epsilon, so we need to try to use a trick. We've already observed that, well, epsilon, let me remind you, it's the ratio of this outflux and the crest flux. It's the efficiency of how self-contained the dune is. How many grains leave the dune compared to how many fly above the crest. And we've observed that these, let's say, outfluxes may have something to do with turbulence. So maybe we could increase this parameter qualitatively by increasing the level of turbulence, and you can try to do two things: increase the Reynolds number by just spinning everything faster, or you may try to lower, there's a technicality of our experiment, lower the driving paddles. If the blades are closer to the dune, then the vortices shed off the tips from the tips of these blades will impinge on the dunes with larger intensity. So we could sort of increase the background level of turbulence. So let's try to do that. We're going to lower the blades a little bit, try to repeat the same experiment. Remember the I think I flipped there's I think there's a problem with the color code here, but it doesn't matter. There are dunes which start close together. Oh no, that's correct. That's actually correct. There are dunes which are close together and they repel. It's quite fast. But they cross the antipodal configuration and they go a bit further away apart and then back closer together and further apart and close together and further apart, close together. After some many experimental hours, they kind of go back to the fixed point. So they converge to it, but in a sort of oscillatory fashion. And if you do the other experiment, you can also see the oscillatory features here. So it seems that we've managed in the lab to also get the second type of qualitative behavior, not a stable node type of attraction, but a stable focus in the dynamical systems language attraction. So at this point, we can be greedy and ask, can we get the third possibility, very large epsilon, unstable fixed point, a saddle characteristic. So we're going to do a crazy experiment where we'll put the paddles even lower down, spin it as fast, well, not as fast as we can, but relatively faster. And now to demonstrate that this fixed point is unstable, I need to start right at this fixed point. So I will start with dunes of equal mass and equal separation. And now you do this experiment with appropriate conditions, and they indeed say, no, we don't want to be equal. One of them gets smaller, the other one gets bigger, and they converge to an asymmetric kind of attractor. So we've managed to collect them all, in some sense, in the lab. Apparently, in that we've observed this okay, maybe a more proper, more proper summary. Two-dune system. Let me remind you that we treat it as in a reduced way as a planar dynamical system. Because the dunes are trapped in a periodic domain, there's naturally a fixed point created. And we made some arguments that the linear characteristics of this fixed point can vary with the turbulence intensity. And we've indeed managed to observe that it can either be attracted in a steady fashion towards the fixed point, in an oscillatory fashion, or this fixed point can be unstable, and the system chooses to go to an asymmetric configuration over asymmetric one. Okay, so that's the end of story number one, let's say.
Karol, I think Daniel wants to ask a question. Go ahead, Daniel.
Yeah. Hello. In the case of the asymmetric state you obtained, you said you increased the turbulence, but you said you had two mechanisms for increasing turbulence. One of which was lowering the pedals even more, and the other one was to increase the speed. Which one which one did you get?
I had to use both.
So you lowered the pedals.
I lowered the pedal even further. Okay, so unfortunately it's a little bit, well, there were two. Unfortunately, I had to change two parameters. So first, from going from first to second, I only lowered the pedal, and that was enough to get the oscillations. Okay. Then I lowered the pedal even further, but that doesn't produce an instability, and you don't want to lower it too low down so it directly interacts with the, you don't want to scoop the dune in particular, and you don't want to have direct hydrodynamic influence. So then at this point, I started spinning it faster, and at some point, you start getting this instability.
Okay.
So I had to use two knobs. That's what you had to do in the lab. Yeah.
But did you try to do a mechanism where you have the pedals way up, like in the other two cases, but only increasing the rotation?
Yeah, that's not enough either. That's not enough either. If you want to get to this crazy, if you want to get to this kind of crazy regime, you need
to have
both.
A lot of turbulence.
It's a very extreme. It's a very extreme thing. Sorry.
You would have to. It's like you're saying that you need to have a lot of turbulence in order to achieve this.
I mean, there are practical limitations. Yeah, and there are practical limitations how low I can put the pedal and how fast I can spin it. Okay, so you can argue that if at some speed it will do it, but also there's some, I don't know, limitations, safety things of the motor that you cannot spin it that fast. So within the constraints of the experiment, if you want to get into the instability regime, you have to turn two knobs at the same time.
Okay, so let me ask an hypothetical question. It's about the number of pedals. Like, if I increase the number of pedals or if I decrease the number of pedals, is there a strong correlation to the increase of turbulence or not? Because I believe if you have too many pedals, it's like you only have like this long, solid shape that doesn't produce any turbulence. But if you have
that's a very good question. That's a very good question. We haven't explored it. I haven't explored it that much, to be honest. The motivation first in our experiment, that it's built in such a way that you can get any integer number between 0 and 12 pedals. Okay, and we always keep 12 because we also would prefer to have homogeneous conditions. You don't want to have, periodic. You don't want to add any periodic forcing. Something obviously, that the dune only moves when the paddle goes by. So we try to keep it as large as possible, but still with these 12, there's a good clearance between them. If we increase them even further, possibly the flow conditions, as you say, would get more quiescent. And yes, there is something about that. Okay, but I mean, in some sense, it's Yeah. In some sense, it doesn't matter, okay? It's just the idea that you want to somewhat project onto this parameter of the dynamical system, and you're just trying to use an experimental trick which are specific to our setup, but that should be a generic property as long as you can tweak the ratio of the sediment flux, appropriate sediment fluxes in a certain way. It shouldn't depend too much on the details of exactly how you generate the flow structures and things like that.
Okay. The inspiration for my question is just that I see the plot, and I mean, it's a beautiful plot, but I'm just wondering if, like, what can we do in the setup of the experiment that's already been made, that we, such a way that we can increase the turbulence so much that we can enhance these structures in the plot, in the dynamical system, for the asymmetric state. Because I'm convinced, but not too convinced, if you know what I mean.
Okay, we'll have to leave it here. If you're interested in more details, hopefully the paper will appear relatively soon. It's been accepted, so
very good.
I'm happy to share it. Okay, so there's so as you see, it's called Summary 1, and there's a second shorter and somewhat lighter story I have, but I don't know if we want to get in there or.
It's up to you, Karol, if you have the energy.
Okay, so I've seen these 2 hours, 2 hour videos in on your YouTube, so we can try maybe, I don't know, another 15 to 20 minutes.
Excellent. I'll let you decide. Feel free to. Yeah.
Okay. So now it will be a slightly different thing, but it will happen in the same setup. So I'll start playing a video. I can also hear the sound from this video, so I will turn my volume down. It's a slightly longer video, so we can relax. People can make a drink. In meantime, it's again a video with a co-rotating camera. So this is one which is mounted to the turntable, and it's looking at something circular here, and the circular thing is an obstacle. So now I've placed in my channel a circle, a cylinder across the domain, and now the dune will migrate, and it's going to encounter an obstacle on its way. So the motivation for it is, you can think of as, this buried house I showed in the first picture, that there is some piece of infrastructure which is on the way of the dune. So the dune is coming. Actually, you can see that there is some sediment which was the outflux from the dune, the non-zero epsilon, the non-zero epsilon caused some sediment to accumulate here even before the dune came, but now the dune came and it's trying to cross our obstacle. I appreciate probably you can see this video somewhat erratically, but hopefully you can see what's happening. Now the dune actually buried the obstacle. It's an interesting the obstacle is cloaked perfectly by the dune. So the flow kind of doesn't know that there's an obstacle anymore, and it behaves just as a bigger dune. But now the surface of the obstacle is exposed again, and the dune is trying to make it to the other side. And it's actually the problem with the co-rotating camera is that it only looks at a certain narrow field, and now we cannot really see what's happening to the rest of the dune, but we can still see that the bedload, the sediment transport continues, and we still manage to transport grains from left to right direction of the flow. And that's more or less it. That's how a dune crosses an obstacle. And this will be the motivation of the the game now will be just to try to put different obstacles. We'll be putting different shapes, cylinders, squares, bridges, and maybe of different sizes, and see how this interaction, what this interaction looks like. So instead of, okay, probably we've had enough of this video, and we don't see the dune anymore. So let's try to take the, oh, sorry, how can I go to the next slide? Okay, that's what happened. The dune came, but the video hopefully worked.
There is just one dune there, right, Karol?
Okay, so now there's only one dune and one obstacle. Instead of dune, we're talking about dune and obstacle interaction.
Okay, all right.
So for simplicity, we have just one dune. It attacks the obstacle, it buries, it cloaks it at some point, and then it moves away. Okay, that's the footage you could capture with the co-rotating camera, and we could also take the all-knowing position of the space-time diagram. It's yet a third way, perhaps, of plotting the space-time diagram. So we've already seen the waterfall plot with lines. We've seen the contour plot in H. Now here H is just corresponds to the grayscale, and the dark things are elevated features. So there's an elevated obstacle here. It's located at fixed position at 0. It doesn't move. And there's a dune which started as far as possible from the obstacle, but it was moving, it migrated, and here it collided with the obstacle. That's what we watched in the video just now. It left some sediment behind the obstacle. You can see that there is some change here. There's some deposit left over downstream of the obstacle, but the dune recovers. There's also a diagram on the right which you can look at in parallel. The dune recovers and it moves away, and next revolution it attacks the obstacle again. Okay, if you remember the gradient of these lines, these world lines, if you like special relativity language, depends on the migration rate. The vertical line it means migration rate 0. That's the obstacle. It doesn't migrate. So the closer you get to the horizontal, the faster moving feature it corresponds to. So the dune was slower before the obstacle. Then it left some sediment, so it got smaller and it's behind the obstacle. So maybe it feels some turbulence now. It becomes faster, and then it a little bit slows down again, and then the process just repeats. You can look at these collisions in time. So hopefully that's kind of clear how this space-time diagram works. And if we understand how it works, we can look at another one, which is just slightly different. It's actually slightly more simpler. So this is it here on the right. There's the obstacle, and there is the dune approaching, attacking the obstacle. Left some deposit, but it didn't recover.
It's dead.
So the dune died. We say that the dune got trapped by the obstacle. And what happened? What do you think is different between these two experiments?
The size of the dune.
So actually the dune, yes, very good. Actually, the size of the dune is fixed throughout everything I'm going to show now. But we changed the size of the obstacle.
Obstacle, yeah.
So it's about the ratio of the obstacle, of the height of the obstacle to the height of the dune. Here, the dune was, well, we measure size of the dune with this area, let's say. So here in the first picture, the dune was significantly larger than the obstacle and recovered almost uninterrupted. The middle is the thing we've seen in the video. The dune struggled a little bit, but recovered. Here, the cylinder is significantly larger than the dune, so the dune does not recover. Okay.
It's about how much mass can be trapped, right?
Yes, so you can look also here are the sort of PTV, the particle tracking velocimetry. This is the kind of average azimuthal, so horizontal velocity in our tank. And these are these three sizes of cylinders. And this is precisely as you mentioned, how much of sand is trapped, because the dune isn't blocked in the way that it comes to a halt and collides and cannot move. You can still move grains over, but they are trapped in this hydrodynamic pocket here, downstream of the obstacle. So maybe, if we are lucky, it can depend only on the size ratio, how tall the obstacle is compared to the dune. Unfortunately, it's slightly more complicated than that. So here, if you look at the middle, the cylinder had actually 6 centimeters diameter. If you take a 6 centimeters, not cylinder, but ridge, then the dune does not recover. It's a sharper obstacle, plausibly, and it created quite a, well, the area of depleted momentum, or the recirculation region, was larger, and we could trap more sediment. So sharp obstacle like a ridge, even if it's of the same height as the dune, manages to trap the dune. But don't worry, if you have a fence like that, you can try to mitigate it with putting a little ramp up or a slide down, and the dune can recover again. And it corresponds also to smaller kind of wake downstream. Okay, so we've seen that the outcome of the interaction depends, first of all, on the dune-obstacle ratio very strongly, but also on the obstacle shape. Also, we've explored the flow velocity, so how fast I spin it, how much energy is input in the sediment transport. It depends on that as well, but relatively weakly. I won't get into that. So these are sort of qualitative observations. Now, can we try to do better than that? Can we try to have sort of quantitative theory, which will, well, some sort of theory which will predict the most likely outcome? And we already suspect that it has something to do with the flow structure. So here's the game. These are all the experiments, almost all the experiments I conducted. I conducted 15. Here you can see 12 pictures, but let's assume it's almost all of them. And now the game is for you to tell me which ones the dunes crossed and which one it didn't, where it got trapped. So I kind of know, but you don't. And based on the of the knowledge, well, on some sort of expertise, you could try to guess where the dune could cross. But at the end of the day, of course, we don't want to have an expert. We would like to have an algorithmic way of determining from this flow velocity data whether the dune can cross or not. Okay.
So is it when the obstacle is cloaked and you have a continuum flow of particles through
okay,
it?
So first of all, these images, I call them images, these flow fields, they were taken without the dune. Okay. And the dune
this is the velocity field.
Complicates everything because the dune comes by and cloaks it and affects the flow field as well. So it's a complicated process. And actually, it's not guaranteed. It's also about the feedback between the flow and the dune and the topography. So it's not guaranteed that these pictures encode all the relevant information. The reality is more complex than that, but that's all the data we have. It's impossible always in this setup. It's impossible to record the flow changes in real time. So we only have the background flow profiles here.
So let me ask you a question there. Before you move on and reveal us the secret, is there motion of the grains at the recirculation zone downstream? Or is it a static pile?
It's to okay, let's maybe go back to a diagram. Sorry. Okay, let's say this one, okay?
Yeah.
There are two things. First of all, it changes the shape of the deposit, even changes a little bit, because initially, if you look just after the interaction, you also can see there was deposit both upstream and downstream.
Yeah.
And then the upstream slowly but surely actually got removed, got wiped away. Similarly, this also gets a little bit smaller with time. If you look closely at the surface, it's more or less static, apart from some sort of turbulent events every now and again moves
intermittent motion.
Yes, there's some intermittent motion, but with a sort of mean close to zero, let's say. So this becomes an close to static pile.
I see. Okay. Okay. All right.
There is that. Okay. Okay. Anything else here? Okay. So now that's the problem of classifying these pictures. Now the question is, what should we look at precisely here? And you could use two approaches. First of them is try to compute something from here based on your fluid dynamics knowledge, maybe, I don't know, the size of this wake or some sort of intensity of the recirculation. Another strategy would be to try to employ some data-driven modern technique and which would tell us what to look at, hopefully.
That's very fancy.
And we're going to use actually this approach because I really tried to do something to come up with something myself, and none of these things worked well. So we're going to use something fancy, but it will be arguably the simplest thing in this family of techniques. There's no big machine learning involved. We're going to just use the principal component analysis, Are people familiar with that? I would assume, I would hope maybe slightly. So just in this context, we'll treat each image as a point, as one data point. I've got 15 data points. If you're counting, there are 12 images, I told you, but I have 15. Each of these images is a point in a highly dimensional space. Morally, it's an infinitely dimensional space, but for us, it will be 8,000. That's the grid. So the grid of this velocity measurement is 200 horizontally and 40 up. So it's 8,000. And now, but I have only 15 data points. So I will, so they can only span at most 15 linearly independent dimensions, and we'll represent each of these data points, so each of these images, in a particular eigenbasis, where the basis vectors are called principal components. Mathematically, it comes from a singular value decomposition of an appropriate data matrix, and these it's partly about, well, one way of understanding it is in terms of low dimensional representation. If you just want to represent your data with one parameter, you could choose the first principal component, then project everything on that line, and the weight of this projection would tell you, or the weights of where it ends up would tell you something about the variability in the data. If you want to have a slightly better representation of the flow field, you can choose two principal components. Okay, so the idea is that they are characteristic features of the data, or which have to do some geometric alignment and location of these data points in the parameter space. So you're choosing a favorable coordinate system, which is somewhat meaningful. Actually, these weights, these components are ordered. I should say, I said the first component, second component. It's because these weights tend to be larger for the first principal component. Actually, the sum of squares is something called the square of something called the singular value. And then the first component has large weights, the second component is slightly smaller, and then they decay and become less and less relevant for representing this data. These are actually the 15 singular values of our data. And this plot is maybe not very interesting. What is interesting is what the principal components look like. The principal components is the basis for the images. So each component is an image itself. The first principal component looks like this. It looks kind of like a mean flow of generic flow around the obstacle, slightly faster above, with some retardation region behind. And this is it. And the weights of our 15 experiments are plotted as these lollipops below. The number of experiments is, of course, random, I mean, arbitrary. But here, the sort of top of this lollipop tells you what shape it was. So it was the small cylinder, largest. The color of the stem is the outcome. So blue, crossed, trapped the dune. Here there were squares, where I also varied this flow velocity. So here you can see progressively faster flows, which project onto this first principal component. Faster flows have faster flow on average around, but still we always crossed the cylinder, the square of height similar to the dune. And here there are some also the ridges, on the other hand, always trapped the dune. Okay, so in particular, this first principal component doesn't tell us almost anything about the outcome, because the trapping red ones can have any value of this weight between, let's say, 40 and 70, and the blue ones too. There's nothing systematic here. However, when you look at the second principal component, which looks like this, it has it's sort of a superposition of a linear shear, sort of fast shear, simple shear, in that it's fast at the top, slow at the bottom, and a strongly localized structure of negative values here. So very retardation of the flow above and downstream of the obstacle. And the weights now, by miracle, have something to do with the outcome of the dune obstacle interaction. So the dunes which, the cases where the dune crossed the obstacle have small or even negative value of the weight of this component, but the ones we trapped have distinctly large, you can actually draw a line which perfectly separates these two. That sort of this, you can see the slide barely made it, but it made it. It's below the line. The centroid of it is below the line. So it turns out, by a bit of miracle, that this second component has encodes some information relevant for the dune obstacle interaction, but it's not unreasonable. You can it plausibly argue that this sort of structure, the retardation of the flow up and the downstream of the obstacle localized, will help if the flow has this property strongly represented. It will help to trap the dune. So that was the dune obstacle interaction story, where we played with the dunes, and by some magic we managed to relate it to the modal structure of the flow. And this is, I think, what did I promise? It will be 15 to 20 minutes, and I think we're actually at this limit. So these are my conclusions. I hope managed to convince you that there are some interesting things about the dunes.
Definitely, yes. Karol, thank you so much. That was a very, very nice talk. It was great. So I now open for questions, comments, suggestions. Anyone?
Great, thank you very much.
Can I ask you a question?
Go ahead, Lou.
Sure.
Yeah, I think these dunes are really fun. So for the for your first part, you mentioned that when you have two dunes chasing each other, one dune chases the other one, there's some interaction term f between the two dunes. But you didn't show. I don't know if I missed it. You didn't show the exact form that you use for the f function. And I also want to ask, if you want to know the exact form of f, do you need to do some fluid dynamics and also granular dynamics study? Because I know there are a lot of granular flow study in Cambridge. So I just wonder what kind of information would be needed to understand how they interact exactly.
Yes, so to understand the interaction function, theoretically it's very difficult. You need to understand the interaction of turbulent flow in this domain with the sediment transport, granular mechanics at the dune. You could try to do a careful experiment where you would measure this interaction term. I actually don't precisely know what it is. Okay. However, now, how did I make all of my arguments in this first part of the talk? All of my arguments were concerned with the linear properties of the symmetric fixed point. Okay, and to know the linear property, the linearization at this fixed point depends only on the following properties of f, on its sign or its value of f, and the value of its derivatives as one of the at this fixed point. And it's sufficient to just assume appropriate signs of them to make these arguments that I've had here theoretically. So it's just at the moment it's just a qualitative reasoning about this, where you try to use as little information possible about this interaction function. It would be great to measure it properly, but I haven't done it.
So you can do that, Karol, because your second line has an epsilon on both terms, and otherwise you would need to know relative sizes of these derivatives, right? In order to get whether your eigenvalues are positive or negative or complex and etc. to characterize the fixed point.
Yes. So I'm not sure I understood what.
So when you analyze your fixed point, you just need the Jacobian, and the Jacobian will just have the derivatives there. But the eigenvalues will depend on the components of the Jacobian. So you get that I minus lambda a whatever equals 0, and then there will be cross products between terms when you calculate the eigenvalues. And there will be some that will lie inside a square root and all that, because it's a square. It's a second degree algebraic equation for the eigenvalues, And for that analysis, you need to know which ones are bigger or smaller, and the products are how these interplays will determine whether you have a focus, whether you have a center, whether you have a node, you have a saddle. But because you have an epsilon on your A dot equation, that's second order, right? And then it depends only on the signs of DFDA and DFDS. I think that's why you can do this.
Yeah, I think I agree generally. Yes. Yeah. So that's this kind of where did I have it?
I think the next slide.
Yeah,
I think you have there.
Yeah, that's the kind of argument. So the miracle here is that the epsilon I have, but I have only in like
there
just epsilon times constant, right?
Yeah.
So that was the argument I was trying to construct here. That, well, if you expand, you look at the tracing determinant.
Yeah. So B1
like you represent determinant as a quadratic of a trace.
Yep.
Okay. I mean, all these J's and A's depend on these derivatives, as you said.
Yes. Yeah.
In some complicated, well, maybe not so in some fashion. It depends on these, on the signs and the values. But now generically, it's going to look like this. So as you now assuming that all of that stays fixed, which, well, is a strong assumption. If you only manage to precisely value epsilon, you're going to trace a parabola here. Okay, that's the idea. That if you keep A's and B's fixed, and you start from epsilon 0, you start at trace A naught and determinant 0. So you start here, and now there are, I don't know, 4 ways of how you can trace a parabola. You can go up and right, you can go up and left, or up, down and right, or down and left. There are kind of qualitatively, well, a few distinct ways of how you can put a parabola. Which one it is depends precisely on the signs and magnitudes of them. But it seems to be that we're doing something close to this one, given that we have first, this region is the stable node, then oscillatory solutions, and then you cross back down to the saddle. Okay.
Yeah. I think that would be what you discussed would be very interesting. I mean, you can prove that it is the case, but what I was wondering is more like the physical kind of interaction and. But I think
that would
for
be,
this particular
that's work to be done. It would be good to know it precisely. I mean, also this is all kind of qualitative. I say, because it's positive or something. I mean, you actually want to know what values the eigenvalues would have, what directions the eigenvectors have. There you actually need to have some proper data.
Very good. Can I pick up on Lou's question before I open for more questions from the audience? Okay. So when you showed us the graph of the focus, the dune spiraled to
look for it.
That one, the green one. So if we think, when we look at these simple dynamical system explanations, we always think about a mass damped system, right? A mass spring dashpot system. And this kind of behavior is basically an overdamped system that has an initial condition with enough inertia that will push you through the equilibrium, and then the spring will bring you back, but in the way it is being dumped, but you still have some inertia, you keep going, and then you're dumped, and you go back until you reach your pi there, so your equilibrium. Would you have an interpretation of what would be the inertia, spring, and dumping mechanisms on your dune?
That's a very good question, and I don't think I have a good answer at the moment. So in this is the, well, so this oscillation is an interplay of 2 variables, the separation and the mass of the dunes. I mean the size. Okay, so the plane where the oscillations happen is the separation, and also one gets bigger, one gets smaller. And now trying to put it into, I mean, to kind of have that oscillator analogy, you would want to have, like, you know, the oscillator have the position and the velocity, kind of, right? These are the two dynamical variables. And here we have, well, I don't exactly, I'm not saying it's impossible, but I would have to think harder how to make this analogy, good analogy of that with a second order differential equation.
Yeah. Probably the flux, the amount of mass that is deposited in a dune would be this inertia. So it got bigger, and then it wants to lose a bit more. But that would be something interesting to see physically what it means, right? Because the math is there. So there should be an interpretation of that.
Yeah, that should be good. It's sort of in sort of frequency of that would be interesting. Yeah, I should think about it.
Okay, all right.
But I believe just a
Daniel,
comment.
go ahead.
I believe the part of the dashpot would be a little hard to make the analogy, because I believe it's an interplay of lots of things, like the very viscosity of the water, and also of the very type of material of the dune.
Okay, so I mean, you're touching on an important point, that it all somewhat results from a complicated microscopic physics.
Agreed.
That there is a complicated way in which the sediment is mobilized, and how these turbulent structures interact with moving grains. It's all a rich subject to study. Now here we are kind of averaging it massively, and we only look at the macroscopic rough behavior of what a pile of sand does, and there we get this behavior. But if you change one thing at the micro scale, like, I know, the size of grains, the type of the density or the viscosity of the fluid, then the parameters of this big system also get perturbed. So you need to, that's something to bear in mind if you want to make analogy between this and other systems outside of experiments. Or
agreed. I have another question before I ask again the audience. So Karol, when you showed us the dune with the obstacle being trapped, there was a spatial temporal diagram in which we could see that the dune survived, that one, so for 2.47, or the one before, actually, the one that you showed before on the previous slide. Is there a steady state for that case?
There is okay, maybe the previous slide will be better.
Yeah.
There's a steady state in there is a steady cycle. There's a steady limit cycle, in the sense that if you start, then the dune attacks the obstacle, crosses, and attacks it again, and crosses, and that is going to repeat periodically, forever in principle. That's, in that sense, the steady state. However, throughout this like in the course of the cycle, the dune doesn't quite reach the steady state, because it keeps getting bigger and decelerates a little bit, and then it hits the dune again, the obstacle again, and then it gets depleted of mass and gets, so that there's some sort of cycle which goes on in a steady fashion. That would be the kind of steady state which we could think of.
Yeah, some sort of periodic steady state.
Yeah, there's a periodic state. That's exactly it. Yeah.
Yeah. So do the grains that flow change? So do the grains that stay trapped change as the dune goes through the obstacle?
A little bit, yes. Do they get changed? Okay. As the dune gets okay.
So there are some particles that are trapped.
Okay. So the particles that are trapped, do not change, but they get added. There's some stuff added on top of it. So you see that there's this residue. There's this residue. The bit which is, if you can see my mouse, the bit which is trapped at this point is lost. I mean, in that it's trapped there forever. If you're trapped here at this point, you will never be washed out, I think. However, there will be some stuff added on top, and that will be washed away. And there's also another sense in which, I mean, in particular, the thing which is stuck in the very corner, I think it's stuck there. But there's also an interesting thing it's a slight effect, but it still happened, that in the same way the dunes interchanged mass over a long time scale, this dune still sheds some grains which get to the deposit, and the deposit also loses a small amount. So there's a very small exchange of grains in the middle of the cycle, but then during the interaction, just some stuff is added and then washed away.
All right, very good, very good. Any more questions for Karol? Daniel, go ahead.
I think I have a little question. It's like a curious question. Maybe I didn't understand properly the setting of the experiment, but never did you see a third structure, as in a third dune forming? Was it just the two? Maybe because of the size of the...
No, that's very good. So I've got two because I put 2 piles of sand, okay? And that was my choice to choose to put 2. Somewhat, you do not observe them, at least in my experiment, to split. So if you put 2
into a third one,
then they will stay 2 more, unless something really kind of, you make one very small, super small, which is outside of this. Well, let's say if you put 2 of reasonable size, they interact, but they stay 2. You can, of course, put 3, 4, or even more. Around 8 or 10, it gets a little bit crowded in my setup. Okay. Now that was I'll briefly just say it. That was the artificial way of putting dunes as piles. There is actually a fascinating whole different topic, that the dunes can spontaneously emerge from a uniform layer of sand. You can put a flat layer of sand everywhere, turn on the flow, you get the surface instability of little ripples developing on the surface.
Yeah, I've heard about that.
They get bigger and bigger, and then at some point, actually, if you have limited amount of sediment, they will the erosion will hit the ground, at which point they separate into discrete number of dunes, and that will be this 8 to 10 dunes. That would be a way of getting there spontaneously. But because I wanted to analyze the 2 dune system in a controlled way, I have 2 dunes because I chose to put 2.
Yeah, but when you have when you have 2 dunes, you never saw a third structure forming, like when you have sediment transporting from one heap to another, like forming a little further apart from the...
Yeah, I understand what you're saying.
Like after the second dune, after the downstream dune, like a little dune forming.
Yes, so the inter-dune, so the transport between the dunes is sufficiently small or sufficiently not intense that they travel as single grains along the burr. They never, if something strange happened and for some reason one dune suddenly shed off a large amount of sediment, that could indeed form a transient small dune in between. Within the setup, we did not observe it. Okay, does that answer your question?
So maybe I'm not sure if in your experiment the pellets, they moved in a uniform manner, but maybe if you did a setup where the pedals started moving and then they spent a little period still, and then you move them for another period of time, like in a nonlinear fashion, maybe I don't know. I'm just
I see you really want to
thinking outside the
produce a
box.
fake you.
Yeah.
Well, maybe there would be a way. So there are actually innate Barkhan dunes, the crescentic structure, the natural structures. They sometimes have this phenomenon that small dunes are born, but it's usually a three-dimensional thing that they split of the
tips.
Spontaneous from the tips.
I think Eric has experiments on that.
Yeah, so Eric, I think Willan could tell us a lot about, and Eric indeed gave a talk, I think, in your seminar too. So also they can be split in 3D due to the interaction. So all of these interactions also have a can have a kind of three-dimensional counterpart, because here where you also can have the dunes laterally offset. Okay. And or they do not have to do a head-on collision, or even if they do a head-on collision, that there is something, curious things can happen.
Cool.
Okay, very good. Danielle?
Cool. Thank you very much.
Yeah,
I think that will be all.
Good.
For the...
No, thank you very much.
Any more questions for Karol? Okay, so Karol, thank you so much for coming, for giving this beautiful seminar at our seminar series. It's a great pleasure to have you here. Would you like to say a few words before we disconnect?
Oh, I think I said enough today. Thank you very much. Thank you for the questions. Thank you for the invitation. It was an honor and pleasure.
Very good. A great pleasure to see you here. So let me see. I think there's a message there. Okay, it is just saying thank you. Karol, all the best of luck for your new, how do I say that? Your new postdoc, right? Your new life at Bath. I hope you enjoy studying crowds and all this kind of things. And hope we keep in touch. Yeah. It's good to see you. Thank you very much, everybody, for coming. And I'll see you around next time. Bye-bye.
Thank you very much. Bye-bye.
Thank you, Karol. Bye-bye.